The topic today will be cross-lingual information retrieval, and the speaker will be Shadi Saleh, a student of mine. So enjoy.
Thanks. Good afternoon. Today I'll be talking about cross-lingual information retrieval approaches and challenges. So again, sorry. Yeah. So first, I will start by defining the information retrieval task in general. By definition, it's the task that in which we want to find some information need from collection. Usually, it's documents, raw text, using some query. That query represents our information need. So I will start by this example. All the examples in this talk taken from medical domain. Here I need to find some information about the connection with nausea, vomiting, and hematemesis. So this is what we call information need. Information need that what I expect the document to contain. But now I will decide to represent my information need in these words: nausea and vomiting and hematemesis. This is what we call a query. So query is the technical term for the text that we type in the search engine when we want to find some information. And now I will move forward to. Sorry. Okay, so I will go to Google as an example here, and I will try to type my query there, and I will get some results. These results, this is monolingual information retrieval task, which means that the query I write it in one language A, it's English here, and the results also in English. As we can see, this is Hitmap. Hitmap it simulates the attitude of the user when they look at the results on the search engine. So as we see, basically we focus on the first results. We don't pay attention to the lower ranked results. We pay attention to the first, usually 2 or 3 results, to some bolded results. Or this Hitmap test was done by Incorio, iTools, and did it. And this is what we call golden triangle. So why we care about this? Why it's important? Because so it looks like 2 meters only. Yeah. Why we care about this Hitmap, or about the attitude of our users? Because we want to see how our search engine or how our information retrieval system is doing, to evaluate it. So I will talk about it more. First, let me show you the structure of IR system. We have some documents, usually from like web document or PDF file or whatever. They contain raw text. These documents will be indexed by indexer. And then we have a retrieval system. This retrieval system is responsible for retrieving the documents from the index that we create, and then reacts to the query that we send to it from its users, and return ranked list of documents. So we started to talk about ranked list from the highest ranked documents to the lower documents. These documents are ranked by the relevance, let's say, value, which means that each document has a score, and this score represents the relevance of this document to that query. So for evaluation, each IR system returns a ranked list of documents, and users usually interested in the top K document. For development, when we want to evaluate IR system, we have some set of documents, and we have some training and test queries. And then we basically we care about % of relevant documents among the highest 10 retrieved ones. Because why only 10 documents? Because users are interested only in these documents. To evaluate the system, we want to judge if each retrieved document, if it's relevant to that query or not, by doing assessment process. So before talking about assessment process, I will talk about the data that we use in this research. We use CLAY 2015 document collection. In IR, we say document collection, but in general, it's you may know it as corpus. For searching, we collected the queries from the IR task in CLAY initiative from 2013 to 2015. They are in total 166 queries. In 2013 and 2014, queries were done by medical experts. How they did that? They used the discharge summaries from hospitals. Each file or medical profile contains the symptoms of its patient and the diagnosis process. So medical experts use these discharge summaries to extract some queries to look realistic. So when we want to find some information about some disease, we try to type in the search engine. We try to type the symptoms that we want to find information about, or the disease. But why here it matters? Because by mentioning medical experts, it means that almost all of these queries contain some medical terms. However, in 2015, the case was not like this. What they did, they tried to simulate more the real case, where normal or let's say non-medical expert person goes to a search engine. Usually we type what we see, right, or what our symptoms are. So what they did, they brought some images. These images contain some symptoms, not medical images. I mean, external images, or like images show bruises or itchy skin, and they showed these images to students, normal students, not from medical faculties. They showed these images to normal students, and they asked them to type what they see. So they described what they see as a queries. So we took these queries and we split them into 100 queries for training and 66 queries for test. I think why we merged these queries, because as you noticed, there's a difference between these two types of queries. So we wanted to implement IR system that can perform well, whatever the case is. Regarding the relevance assessment, it means that the process that we want to see if the returned documents are relevant to the query that we type or that we search for or not. Or it's more correct to say the information need, because as you saw in the previous slides, there is difference between the information need and the query that we type. So for here are some examples from CLAY 2013. Here's the description of the query. Title. We use title for the query, for querying. So this is the query. This is the description. This is what we really need to find. And here are more information, like more narrative description or more description about the query and the profile of the patient. In 2015, we don't have this description, we don't have this information because the students looked at some pictures and they typed what they saw. So as you can see, we see like simple English without any medical terms. Here are 3 examples from 2000, like simply red itchy eyes without red patchy bruising over legs or nail getting dark. Simple English without any medical, complicated medical terms. So for assessment process, we want to judge, we want to see how our IR system is doing. So what we do, we install a tool for assessment. Here we have all the queries, and here we have some documents. These documents were taken from different systems we implemented, and then we ask medical experts to look at each query, and then to check the relevant documents, or the return documents for that query, and to decide if this document is relevant to the information need that is represented by this query or not. There are more decisions. I will talk about them. So this is sample query, the same query that we see. So we ask the medical experts not to look at the query itself, but to look at the information need, to judge if the document is relevant or not. And basically there are 3 or 4 judgment. 3, sorry. Unjudged, they haven't done this yet, or this document is highly relevant to the information need, or somewhat relevant, like it answers partially the information in the information need, or it's not relevant at all. So they looked at each query and the return documents for that query, and they started to judge. So as this is example, I think this is a relevant document. I'm not expert, but yeah, this document was returned because it contains some terms from the query, like nausea and vomiting, but without hematemesis. It means that the vomiting of blood. So this is general vomiting, not the case. And this is the main challenge of IR. This IR model is based on term matching. We see that we check the terms in the query and the terms in the document, and then we calculate the similarity between them. Since the model that we used found some terms in the document which are already in the query, so it returned it with a high score. But unfortunately, it's not the case here. Yeah, so this is the assessment process, and we have done this process 2 times. Last year, we assessed about 1,500 documents, and last July also we assessed almost the same amount of queries, of documents, sorry. And now we are running also assessment process for something around 10,000 documents for a huge set of experiments. So for monolingual experiments, for monolingual IR, we indexed the collection using Terrier. It's open source IR system available online. We conducted a set of experiments to tune our model to select the best model for retrieval, or to select the best parameter for this model for our collection. We mainly focus on % of relevant relevant documents among 10 return documents, highest return documents. So according to our monolingual system, we have 47.10 for training set and 50.30 for test set. Training set around 100 queries, and test around 66 queries. Now we move to cross-lingual IR. In cross-lingual IR, at the beginning of the internet, almost all the web content was English, and then especially last decade, many languages started to grow more significantly than English. Like German, for example, I think in 2007, something like this, the amount of growth for German language was pretty huge. So in that case, that we have some here we have some barrier between the user that who wants to find some information on the internet, and the case that this information are not available is not available in his language. Like I move to Czech and I want to find some information about public transportation system, but I don't speak Czech. So here's the main problem. What should I do to find this information? And this is what Crosslingual IR tries to solve. Here's the same query written in Czech. So what we do, maybe the easiest solution. Here I have some Czech query. I use some empty system to translate this query into the collection language. Here is English, but I don't speak English. Here I speak Czech. So I translate the query into English using some empty system. Then I send this translated English query to IR system, and then I got a list of documents. As you can see, these documents are in English. We can do more. We can translate these documents into his language, or we can let him decide if he wants to translate to use their own empty system or not. And by doing this, we have reduced the cross-lingual IR task into monolingual task. Because from this point, we have English query, we have English collection index, and we have the same IR system. So to conduct cross-lingual IR experiments, we translated the 166 queries we talked about into these languages, 7 languages: Czech, French, German, Hungarian, Polish, Spanish, Swedish, by asking native medical experts to do so. So since the task is reduced to monolingual IR, we use the same relevance data that we have in monolingual IR. But as I mentioned, we conducted a set of experiments, cross-lingual experiments. But the approach is same, that we have English query and English document. And the assessor has to decide if this document is relevant or not. So I will start from using some available public online MT systems to translate these queries into English. I used Google Translate and Bing translators, as you can see, for all of these languages. Here I added mono results, so you can see they are the same because I have only English queries, just to compare each system with the monolingual results. So Google is doing well, but not with the Swedish language. Now, our baseline cross-lingual IR system uses SMT systems here developed here in UFAL within Key Connect project, and these systems are trained to translate queries in the medical domain. And why I say the queries, not sentences, because queries usually are short, and they are not written in correct language, right? Like when I search for something on the internet, I don't use correct language. I don't use like the full sentence or the correct order of the sentence. I just type some set of words together representing my information need. Also, this system is based on Moses, so it returns list of alternative translations, or we call it in-best list, scored from the highest scored translation to the lowest one, and the highest translation here is scored to be give to give sentence in correct language, not in. I mean to be used for humans, not for clay usage. And here are the results. This is the baseline that uses the best translation from this list for all the languages. Still, Google. Gives the best almost for all languages. The baseline system uses the best translation from best list. Like we translate the English query, the Czech, for example, query into English. We have a list of alternative translations. We use the highest scored one, best translation. We create a query from this translation, English translation, and then we do mono IR. So here we have some what we did here to see if using best translation is a good solution or not. We translated each query into English, and then we got from best translation into 20. We choose this number after some tuning experiment, and then let's say hypothesis 1, hypothesis 2, hypothesis 20. Then we use each one of these hypotheses to conduct retrieval. Like baseline system uses only best translation, but we used all of them separately. And for each of them, we conducted retrieval, and then we calculated P at 10. After doing that for the training queries and for all languages, Czech, French, and German. As you can see here we have 3 languages, and these are the ranks for the queries. Like here, it means the number of queries that gave the highest P at 10 by using this rank. So we have here 50 queries. In 50 cases, we got highest P at 10 by using only best translation, which means that in 50% of our queries, we couldn't achieve the best P at 10 because we are looking only at the best translation. So here was our motivation to look more into this problem. We are interested in these translations to choose the best one to give better results for cross-lingual IR, not for like for human reading or. Sorry. So here we designed reranking model. This reranking model is doing the following. We have this English query. This English query, Czech query. It translated into English using SMT systems. Then we got n-best list. From this n-best list in English, we re-rank this list to get the translation that might give the highest P at 10. So we are not using here the best translation anymore. We are using different translation according to our re-ranking model. And then we use this translation as an English query to do retrieval. To train this model, we use some features. First, we took when we translate some sentence using Moses, we can turn on the verbose output of Moses and get all the scores that were used to calculate the scores for each translation. So we used all of these scores, translation model, language model, reordering models. And then we added a new feature, rank feature. It means that if this translation is the best translation, we add 1. Otherwise, for other cases, we add 0. So it's Boolean feature for the rank. And also, we used features based on blind relevance feedback. What does it mean? That it means it's more likely that the best translation is the best one for cross-lingual IR. According to our experiment, in 50% of cases, it gives the highest P at 10. So what we did, we used this best translation. We call it best list, one best list. We use it for retrieval. And then we got set of documents. We took highest 10 documents from the collection. And then we merged these documents together. We created the pool, back of words, by merging all of these documents together. And from this pool, we calculated term frequencies for each term. Now back after creating this pool, back to the hypothesis. Each hypothesis, for example, hypothesis N, it contains some words. So we summed up the term frequency for these words from this pool. And then we used the IDF scores for these terms from the collection. IDF score, it tells us how much this term is important in the collection. So we added it to the we summed the IDF scores for all the words, and we added to the feature vector for that hypothesis. Also, we did the same here, but using translation pool. We merged all the translations together. We created pool from these translations, and we calculated term frequencies for each term. We used also retrieval statute value. Actually, it was the most significant and important feature in our set. What it means, here we have set of hypotheses or alternative translations for each query. For each one, we used each one to conduct retrieval, and we got the highest scored document. This document has a score, like a relevance score to this hypothesis, and this score is called retrieval statute value. We added to our feature set for each hypothesis. Also, we use features based on external resources like UMLS and Wikipedia. In UMLS, we used UMLS in 2 ways. First, we calculated how many terms we have in each hypothesis that they exist in UMLS meta-desirous, because it's medical dictionary, and we want to see if the hypothesis contains medical terms or not. The second way, we used a Hitmap tool it's available with UMLS tools. Hitmap can annotate the queries, the sentence or any term with medical concepts. From huge meta-desirous. So we calculated how many concepts we have for each hypothesis, and we added the number of concepts into our feature. Also, we used Wikipedia. It was similar to the blind relevance feedback. We indexed Wikipedia. We did retrieval using best translation, and then we took the highest 10 ranked articles from Wikipedia. We merged them together. We created pool, and then from that pool we calculate term frequencies for the hypothesis terms. For training, we used 100 queries. after some tuning, I showed to you 20 hypotheses just for like as a representation for the distribution. But after some tuning, we used only 15 alternative translations for each query, and we followed two approaches. First, we created model for each language. We call it language-specific model. And second approach, we used language-independent model, like one model for all languages. And we used leave one out cross-validation because we have only 100 queries, so it was not sufficient for splitting the queries into test and train. So what we did here, we used 99 queries for training and one query for testing. Now, for the final test, what we do, we generate vectors for each query, vector for each hypothesis for each query, and we train regression model. This regression model can predict each hypothesis how much p at 10 will be when using that hypothesis. And then after getting the highest scored hypothesis, we use this hypothesis for retrieval. Here are our results. Here we used language independent model, which means that after we translated the queries for each language, we merged all the translations, all the alternative translations together from all languages, and we trained one model for all languages. As you can see, we have here a significant improvement over Google, Bing, over our baseline system, and here even over the monolingual system. In general, we have here 9 queries improvement in Czech, 15 queries in German, and 8 queries in French, and we have some degradation. So I will show you some examples here. Here, reference, this is the monolingual query, the original English query. And here we have the Oracle hypothesis, which means the hypothesis that will give the highest p at 10. Here are p at 10 values for each query. And here's our baseline query, or using best translation. And here, best hypothesis using reranker model. So as you can see here, we can see some problem because of the morphological forms of each for the query. We didn't do any morphological processing. So facial here is different from face, and cuts different from cut, scar tissue. So here, we were able even to outperform for this query the monolingual IR using face cuts and scar tissue. Here, in this query in French, COPD, I think it means chronic obstructive pulmonary disease. By adding this word, disease, to the query, it improved the baseline system and even the monolingual system here. Here also we have same case. We used reranker used operation instead of surgery, and it's not correct. It's not used. Usually, it's not used operation instead of surgery. So that's why we see here results are. Result here is less than reference or even the baseline system. Here also here we have improvement, swollen lower limb. This is the best hypothesis. It's similar to the baseline system. We couldn't choose better hypothesis, and this hypothesis gives the highest p at 10, leg swelling. Now, Now, after we finished these experiments, we got queries in more languages: Spanish, Hungarian, Polish, and Swedish. Also, we have SMT systems available for these languages. So, what we did first, we expanded the translation. We started first with Czech, German, and French. We didn't have translations for these languages. So first we translated all the original English queries into these languages, and then we started to check if our reranker can do the same with these languages or not. First, we merged the data from old languages, Czech, French, and German, and also we added data from these languages. What was challenging here that these languages, after we run all of our experiments, we asked medical experts to do the assessment. So these languages were fully assessed. While here for these languages, only between 65 and 70% of highest 10 documents were assessed, which means the unjudged documents will be treated as irrelevant, and it might not be the case. Maybe they are relevant or not. So here we didn't have enough assessment for these languages. That's why using these languages, which were fully assessed, was significant to create data for this model. So we took data from these languages. We added data from one data set from these languages to each model, and then we also trained language-independent model and language-dependent models as we did before. So again, our reranker also outperformed the reranker, Spanish, Hungarian, Polish, and Swedish. Here we have here, we didn't improve the Polish system. However, you can see that the baseline system is not good comparing to Spanish and Hungarian. The same case for Swedish, even though here we improved by 2 points for Swedish. So I was talking about query translation, the case that we translate the query into the language of the document. Here we move to new experiments. We want to translate to check if we translate the document collection into query collection, if the results will be better or not. Actually, according to a lot of studies last decade, like they ended up with the following statement: document translation is better than query translation, like something like 15 years ago. So because lots of improvement occurred to SMT systems, we wanted to check if this statement is correct or not. So what we did, we took the queries, translated by human queries in these languages, and then like we kept them as they are, and then we translated the English documents into all of these languages. Here, for example, we translated these documents. They are almost 1 million documents. We translated them into Czech, and after translation, we created index for these Czech documents. So we have Czech index, and we use the Czech queries to do retrieval from the Czech index, and then we got ranked list of Czech documents. What we do also, we did morphological processing. After translating the documents, we stemmed them using a snowball stemmer, and also we lemmatized both queries and documents. We lemmatized them using tree tagger for French and German, and morphodata for Czech. So now we have 3 experiments. We have document translation without any processing. We have document translation after stemming, and we have document translation after lemmatization. Here we cannot really trust these 2 experiments because currently we still have ongoing assessment process. So the average here is about from 60 to 70%. So we cannot finish this finding. We cannot say that stemming is better than by doing stemming we can improve the document translation, or lemmatization cannot improve. It's better than the without lemmatization, but it's not better stemming. So it's not final result. Actually, we still have now ongoing assessment, and we expect it to be done at the end of December. Now moving to query expansion. As you saw from the first slides, we think about some information need, and then we type this information need as a query in search engine. In most cases, maybe we are not lucky to type the correct queries, or we cannot choose the correct terms for that. So query expansion is the process to help automatically the users to add more terms into their query. So here our approach is based on machine learning model as the following. We got 20 best list translations for each query, and then we create a pool from this translation, and this pool contains, let's say, candidate terms. So by merging all of these hypotheses, we have here in terms, and we already have best translation. So we want to add some terms from this pool to this query to see if we can improve the results or not. So the model is required to predict which terms we can add to the original translation to increase P at 10. Actually here predict more than terms. Sorry for this typos. What we did, we first we try to add multiple terms, 1 term, 2 terms, 3 terms to the original translation, and to check which of all of these new queries can give choose the one that will give the highest P at 10. And as features, we used IDF from the collection, term frequency from the pool, translation pool, and also we use similarity between term and query, or the best translation, using word embeddings. What we did here, we summed the word embeddings for each term in the query together. So we have sum for all the embeddings, and then we calculated cosine similarity between this sum and between the candidate term, and we added this score to the features. The main problem here was with the limitation of translation pool. Like for some cases, after we merged all the terms from translation pool, we couldn't have enough terms to expand the query with. So what we did here, we expanded the pool from Wikipedia. We used best translation to retrieve documents from articles, from Wikipedia, and then we from only abstracts from Wikipedia, and then we added this 10 articles from Wikipedia to this pool. Yeah. Here are the results for query expansion. As you can see, also it's still ongoing assessment. I cannot confirm these results yet, but I can show you some. Sorry for this alignment. Actually, I don't use Acrobat Reader usually, just when I use projector. So query expansion improved about 10 queries in general, but we have only 60% of coverage. So here are some examples. For example, here the monolingual query is white patchiness in mouth. P at 10 for this query is 10. Here's the baseline system, best translation for this query. I'm taking these results from check system. So baseline system translates the check query for this English query into English, and then, sorry for this confusing. Baseline system 10. Here we added 2 terms into the baseline translation. We added 2 terms, oral cavity, and we improved P at 10 from 10 to 70. Here's different example. SOB, P at 10 for this query 50. Dysphonia for baseline. And here we added 3 terms: rash, breathing, dyspnea. We improved P at 10 from 60 or even from 50 actually for mono, or 60 for baseline to 70%. So that was everything. I presented the monolingual IR system evaluation and assessment, and I talked about cross-lingual IR approaches, that we follow the query translation approach or document translation approach, morphological analysis, query expansion based on translation pool and Wikipedia pool. Also, I presented reranking model to re-rank the alternative translations from SMT systems for better cross-lingual IR results. Also, we plan to, after we finish the assessment process and after we translated the queries into 7 languages, we plan to release a new data set with the assessment and the translations. Thank you so much.
Thank you very much for your talk, and I think this is a right time for the discussion. So, are there any questions?
Hi, thanks. That's a lot of experiments you did. When you're trying to use the n-best list in the translations, so I understand it that you still do this kind of independently for each of the items in the n-best list. So you just, in the end, you choose one translation as the best translation to use for the search. Because you, so you would the default is to use just the best translation, and you just re-rank the translations, and then you still use like the top translation from your re-ranker.
Yeah, I get the n-best list. I re-rank them according to P at 10 objective function, and then I take the highest scored one after re-ranking them.
So I wonder whether it would be possible to do it even like after that. So to do the search for the, let's say, the 10 best documents for each of the translations in the n-best list, and then maybe re-rank the results of the IR, so the search results, because maybe you could also do like voting, that if 5 translation all return the same document, so maybe this is some good feature for the document.
Yeah, that's a nice idea.
Yeah, but I don't know actually. That's my other question. So how good are the n-best lists? So I heard that people often complain that the n-best lists are not very interesting, that they are all very similar translations, that there is not much diversity. So I don't know how this looks in your case.
Yeah, that's correct. What we did, we during translation we turned on distinct parameters. So even though we got like, as you said, like 10 hypotheses with the similar words but different reorder. So it was the case for some queries, but I think as I mentioned here, the same problem appeared when we used query expansion. Like for all the hypotheses, we almost had the same same terms in the original query. So in some cases, yeah, that's correct. They were not really rich with different terms or different synonyms for the original translation. But back to this. Back to this figure. By re-ranking them here, we got, like in 50 cases, we got we got here a hypothesis give highest p-attend than the best translation. So which means that, I mean, it's large number of and of course here we don't care about ordering in IR. So which means that there were some informative terms in this hypothesis.
So do you do some like so in the re-ranking you took top 15 translations,
yes, 15
I guess.
after tuning, yes.
So do you remove the ones that only differ in the word order or not?
In word orders and some punctuations. So you they are totally different. Like in some cases, we used 100 hypotheses to create 15 hypotheses.
Yeah, sure. Thanks. Nice.
Thanks.
How many relevant documents appear in 10 top documents?
Yeah.
They are not weighted for the rating that the first document is the greatest.
Exactly. No, it's not.
Just
if they are relevant or not. Yeah. Here's the case. So here we have relevant, not relevant, or somewhat relevant.
Okay, so one question from me as well. Can you go to slide 25 or 24, where you show the results of the re-ranker?
25?
Yeah, the re-ranker results, maybe 24.
For
yes,
these languages?
This is the slide. No, that's not the one. Can you go back a bit? No.
Sorry, I'm still confused about this.
Yeah, this is the one. So this clearly shows that in some cases the re-ranker is better, even better than the monolingual system, right? So can you comment on how this is possible?
Okay, this was happening. Like in some cases, we translated the query from Czech into English. We got list of translations, and in, let's say, the best hypothesis that gave the highest p-at10 contained some synonyms on some medical terms. These medical terms didn't appear in the monolingual query. And why this happened? Like we have the English query. We asked some medical humans to translate these queries into Czech or into German, French, whatever. And then they translated these queries, but using their own knowledge. I mean, their own way of representing these medical terms in these languages. And then we took these translations from these queries in Czech or French, and we translated them again. So after translating from English to Czech using medical experts and translating them back from Czech to English, new terms appeared because maybe they changed, they contributed to the translations without knowing that, or maybe we have from the data that we have in the monolingual the data that we use to train the SMT systems. We have some data, and some medical data, in which some new acronyms or synonyms for this query appeared, and this improved this added more information to the query.
Any other questions? If not, let's thank the speaker again for the nice talk.
Thank you.